Hi, and welcome to part two of this unit's notes. We're going to be talking about the rotation and revolution of the Earth. Last set of notes, we talked about the distance between the Earth and the Sun, and the atmosphere, the little dust particles, and all that stuff between the Earth and the Sun that affect climate and the temperature of the Earth. The relative positions of the Sun and the Earth, though, those positions compared to each other, determine whether it's day or night. Pretty obviously, determines when the seasons change and climate differences between places at different latitudes. So let's get into that. First, as the Earth moves through space, it rotates, meaning it spins on its axis like a top. So it just kind of twirls like I don't know what, like a ballet dancer that puts her hands up in the air, and I don't know what that's called. But anyway, that's rotation, that's spinning, twirling. Each rotation lasts 24 hours, and that equals a day. When our part of let's say if the sun is over here, it is going to be daytime over here, this area that's facing the sun, and it's going to be nighttime over here, this area that's not facing it. And then as the Earth continues rotating, that will change. And every 24 hours, it goes all the way around. Whew, good. You totally knew that from third grade science. I don't know why I'm telling you that, but now you know it again. Good job. Next, the axis that it spins on. You can, back in third grade again, they probably told you that the axis was like a straw that went through an orange and then it twirled around the orange. Okay, if that's how you remember, that's okay. But it's an invisible line. Again, it's kind of a direction, or it's what you could say the center that the Earth rotates around, but it's not actually a real thing. It's not like there really is some kind of physical structure that is the axis. It's just the place that is like the center of the spin. Goes basically from pole to pole. The axis does wobble the same way that when you look at a top spinning around on the floor, it does these little miniature wobbles, which can do kind of weird things, like say point the North Pole in different directions. So right now we've got a star that's directly above the North Pole that we call the North Star, but in the future this axis is going to keep on kind of wobbling. So in the future the North Star is no longer going to be above the North Pole. It's going to be over here or something like that. Some other star is going to be up here, or no star at all, which will make navigation without compasses a little more difficult. But anyway, that is the Earth's axis. So if the plane of the ecliptic here, that refers to like the solar system. So here's the sun again, and the Earth goes all the way around it, and all the way around it here. So the Earth also revolves. In addition to rotation, it revolves around the sun like a track runner. So that's moving through space as opposed to twirling in place. One revolution takes about 365 days, about 365 and a quarter rotations of the Earth equals one revolution. That is in time. It's not like those movements are directly convertible to each other. This graphic here is, it's kind of useful in that it shows a revolution. But don't imagine that these are the actual relative sizes of the Earth and the Sun and the distance. Like if this is, right here, the real size of the Sun, then the Earth should only be about like that big or something. Because the Sun's diameter is about 100 times the Earth's diameter. So you could fit 100 little Earths like this across the Sun. So the Earth is obviously going to be much smaller, and it's going to be much farther away. Like we said, 93 million miles. So way over here off the screen, a tiny little dot. That's the Earth. But other than that, this is, hopefully this helps. And now you need to keep in mind that, due to the wobbling, the Earth's axis relative to the sun is not straight up and down, but it's tilted about 23.5 degrees. So, again, if the sun is over here, the Earth is going to be rotating along like this. Not going to be, rotating flat like this. And that is important because it means that the sunlight strikes different parts of the planet more directly and for longer periods of time at certain times of the year. So for instance, right now you can see the Earth's axis, and again this is very much not drawn to scale. The Earth's axis is like this. The Earth is going to be rotating like this, which means that if here's the equator, it means the southern part of the world, the Southern Hemisphere, right down here, as it goes around and around, rotating, is nevertheless going to be more exposed to the sun's rays. You can see that's, it's summer there in the Southern Hemisphere, so it's getting a lot more direct rays of the sun. The Northern Hemisphere is a little more protected from the sun's rays. And this this means that there are certain times, like say June, where the Northern Hemisphere, that half of the planet, I think you know that word, leans toward the sun and it has summer while the Southern Hemisphere has winter. Like in the last slide we saw over here, the Northern Hemisphere has winter because it's kind of tilted away from the sun. The Southern Hemisphere has summer because it's more exposed to the sun. Now over here on this this graphic, it's like we're looking at the Earth and the sun from the opposite direction. So over here on the left, the Northern Hemisphere is getting much more of the sun's rays, something to keep in mind. The day in June that the Northern Hemisphere is most directly pointing at the sun is the longest day of the year for the Northern Hemisphere, including for South Carolina. That day is called the summer solstice. The opposite of that, the winter solstice, occurs in the Northern Hemisphere after the Earth has revolved halfway around the sun. It's taken half of a year to get there. All of a sudden, well, not all of a sudden, slowly, it became December 21st. So the Southern Hemisphere is now most exposed to the direct rays of the sun. It's getting hot in the Southern Hemisphere. The days are lasting a long time. This, for the Northern Hemisphere, is called the winter solstice, meaning it's the least sunny day that we get, and very often a sign of serious cold. So if you have two solstices, you also have two periods of the year, 2 days of the year, when the north and the south are equally facing the sun. And if you have the northern summer solstice there, the northern winter solstice here, between those times, you have what in the north, going from winter right here to summer right here, it's going to take you through spring. So you have what's called the spring equinox, or equinox, you can say it either way. And on that day, once again, the Earth's axis is still at a slant, but the slant is not running towards or against the sun. And that's your spring equinox. Obviously, as the year goes on, you spend another quarter of the year getting your way to the summer solstice, and as summer heads into autumn, you have your autumn or fall equinox, when once again the Earth's axis is not pointing either the southern or the northern hemisphere towards the sun, and they're both getting equal radiation from the sun. All right, good job. You've learned a bunch.